Hey there, this is Professor Shannon Gracey from Miracosta College. Today we'll be covering section 3.3 from the Larson and Edwards Calculus text. If you're interested in also downloading the guided notebook, it's at www.mathchick.net. All right, so here we go. Today we'll be focusing on how to determine the function intervals on which the function's increasing or decreasing, and then we'll learn how to apply that first derivative test to find relative extrema of a function. All right, so let's get started by warming it on up. We need to find the equation of the line tangent to the function f at x is equal to tangent at x at the input value 3 pi over 4. So ready, on your mark, get set, go! You can do it. I know you can. All right, let's see how you did. So to start it off, what do? There's a couple things we can start with. Okay, let's go ahead and start off by finding the slope. We'll find the slope at x equal to pi over 4, and that is, of course, we're going to find or evaluate f prime at pi over 4. Okay, so here we go. Our function is f at x equals tangent at x, and differentiating both sides with respect to x, we'll have f prime at x on the left side, and then what will we have on the right side? Beautiful, we'll have secant squared at x on the right side. Now we need to find f prime at pi over 4, so we'll have secant at pi over 4, this quantity squared, and then we'll have the square root of 2 squared. So the slope of the line tangent to this function when x is pi over 4 is 2. Good so far? Awesome. Now just a couple things left. We need to evaluate f at pi over 4, so we know which y value to use. And f at pi over 4 is equal to the tangent function evaluated at pi over 4. So we'll get f at pi over 4 is good, 1. Thirdly, we will write the equation of the line tangent to f at the ordered pair. What did we find? Beautiful, pi over 4, comma 1. We'll have y minus y1, so our y1 is 1, is equal to the slope, which is 2 times x minus x1, which was pi over 4. So this is what we matched up. This 2 represents our slope, and that was f prime at pi over 4. And then this y value, we highlight this part, f at pi over 4, and the input value was given in the problem. And we're all done. How'd you do? Awesome. Feel all warmed up and ready to go? Woohoo! Okay, let's do it. All right, so increasing and decreasing function intervals. So basically, a function is increasing if, as x moves to the right, its graph moves up, and it's decreasing if its graph moves down. A positive derivative implies that the function is increasing, because remember, a positive derivative means a positive slope, which implies increasing movement on the graph. So that means a negative derivative implies that the function would be decreasing because it would have a negative slope. The function would have a negative slope there on that interval. So the official definitions are here. So again, this is saying that as x moves from left to right, that means that the function is going up, and that's for increasing. As x is moving from left to right on a decreasing function, your y values, your function values, will be dropping, going down. Okay? So, here we go. There's a test for increasing and decreasing function intervals. So this test, it should be pretty intuitive. This test is basically saying that, hey, if you've got a positive derivative for all these x values in the open interval from a to b, then your function is increasing. If the derivative is negative, right, then the function is decreasing. And if you've got an interval where you get a zero derivative for all those x values in the interval, then your function is constant on a to b. So let's take a look. If you take a look at this graph, right, this is our original function here on this graph. So what this is saying here is that on these input values, right? So let's think about what's happening. So we've learned a lot of stuff, okay? We've learned that relative extrema only exist at critical numbers, right? So here, this right here, wherever this is, call it C1. And then this guy over here, I don't know, it's about right here, call this one C2. And it appears this is equal to -2, and this is equal to +2, right? So what does this mean? This means that on this domain here, right, what's happening? So I'm looking at that middle interval. Well, no, let's not do it that one first. Okay, so let's look at the graph. Would you guys agree that as we move from left to right until we get to right here, C1, would you guys agree that the graph is decreasing, right? And so what's going to happen is you're going to have negative outputs for your derivative on the interval from, actually it implies that we'll be increasing in this manner, right? So basically what we would find is we would find that on -infinity to -2, f prime at x is less than 0. So if you made a number line, right, and you were testing values, and you had a number line that looked something like this, and you had your critical numbers on this number line. So call it -2 to +2, right? And you could basically make your intervals here -infinity to -2. See, like we just did right there. What would the next interval be? Good. -2 to 2, and then 2 to infinity. Okay, so far? So from -infinity to -2, every single value, right, on that interval that you plugged into your derivative function would test to be negative, right? So you test your f prime at x is going to be negative on that interval, okay? Let's check out what we think is going to happen on the other intervals. So going from here to here, what's happening on our graph? Do you see how it's going up, right? Whereas over here it was going down, right? So since it's going up like that, what does that imply? That implies that on the interval from -2 to 2, f prime at x is greater than 0. Groovy so far? So what would we put in here? Oh, we'd put a positive. And then now, as we move from 2 on to infinity, what do you think is going to happen? Good, we have this decreasing behavior, right? So what does that mean about our derivative function? It means that on 2 to infinity, f prime at x is less than 0. So we would put a negative here in this number line. So this is a way where if we did not have the picture of this original function, so this was our x and this was just f at x over here, right? So if we hadn't had the picture of this function, right, then we could have used just a number line and the critical numbers, which divide up the number line into intervals, to find out if the derivative was positive or negative, and then made our conclusions. So what would our conclusions be? Good. There's some different ones. It's at C1 equal to -2, f prime of x is equal to 0. Over here at C2 equal to +2, f prime at x is equal to 0. So if we want to figure out, some kind of a conclusion, we can say f is increasing on the interval from, beautiful, -2 to 2, and f is decreasing on perfect, -infinity to -2, non-inclusive, union 2 to infinity. And that would be, the end result of this particular problem. All right. So, here's some guidelines, right? If you don't have that graph right in front of you and you're looking for some guidelines on finding intervals where a function is increasing or decreasing, here's what you do. So first off, we locate the perfect critical numbers of f on the interval or in the interval from A to B, and use these numbers to determine the test intervals. So when you see our number line we made, that's where we figured out these intervals here, from minus infinity to -2, -2 to 2, and 2 to infinity. We broke up that number line using the critical numbers. All right, and then you determine the sign of which function? Perfect. F prime at one test value in each of the intervals. And then I'm just going to put in parentheses, not using the critical numbers, because what will you get in your derivative test there? Good, you'll just get 0. That's how you found your intervals, or one way you found your intervals. How else do you find critical numbers? Perfect. Input values where the function exists but is not differentiable. So then we use the test for increasing and decreasing functions to determine whether f is increasing or decreasing on each of these defined intervals. All right, so you can use this if you've got, infinity or minus infinity as part of the intervals as well. Okay? All right, so let's put this into practice. And really, I did my, the illustration, the figure here. Okay, so there you go. Okay, so identify the open intervals on which the function is increasing or decreasing. So here we go. What do we do first? Find the critical numbers. How do we find critical numbers? Well, first off, we can find the derivative and then set it equal to 0. Okay, now look at this function. What kind of function is it? Good, it's a polynomial function. It's got smooth curves, so there's not going to be any value of x where this function is not differentiable. So we just need to find the zeros of the derivative function. So let's do it. We'll get perfect 27 minus 3x squared, and then setting the derivative equal to 0, we will have 27 minus 3x squared equals 0. And then adding 3x squared to both sides, we get 3x squared is 27. Dividing both sides by 3, we get x squared is 9. And then square rooting both sides, we will have x is, beautiful, plus or minus 3. Good so far? So now we look at our interval. Well, we weren't given one, right? And the domain of this function is from minus infinity to infinity. So what are we going to get? We're going to get C1 is -3 and C2 is +3. Okay, then we run the test. You need to show me how you're running the test. So the way you show me is you make yourself a number line. You show how it's divided up by your critical numbers. You would also include any values where there would be discontinuities or vertical asymptotes, any kind of stuff like that where the function doesn't exist. So any domain restrictions would be included on the number line. All right, so now we get these intervals. What will we have? Good, minus infinity to -3, -3 to 3. All of these are non-inclusive. And then 3 to infinity. So you get to your original f prime, right? So f prime at x was 27 minus 3x squared. So you go to the one before you found the zeros, okay? Now, what's next? Good. You're going to find a test number in each of these intervals. It can be any number in the interval except one of the critical numbers. So what should we pick? Well, How about -4 on this one? We'll do that as our test number, right? And then 0 might be good in this interval, and then 4 might be good in this interval. So f prime at -4 is equal to 27 minus 3 times -4 squared. Now, one thing that you need to, or you don't need to, but that you might want to remember is this. We are only interested in finding out whether we end up with a positive or a negative result, because that's what we're testing for. So if you can see clearly that something's going to be positive or negative, you could make your results you could make your conclusion a little bit more quickly. So f prime at -4, it's going to be, so we'll have 3 times positive 16, right? Because that negative will square away, and that's going to be 48, good. So you're going to end up getting 27 minus 48, right? So that is clearly going to be negative. So here we're going to put a negative. So every input value evaluated in the derivative function from -infinity to -3 non-inclusive is going to be negative, which means our function is decreasing on that interval. Good. All right, let's go on to f prime at 0 is going to be 27 minus 3 times 0 squared. So again, we're plugging the value of 0 in to x on the derivative function. And this one, I hope you can see, will be positive. So we'll get a positive result for every value that you plug into the derivative on the interval from -3 to 3 non-inclusive. Groovy. All right. So now let's do f prime at 4, and that's going to be 27 minus 3 times 4 squared. And do you see, we'll end up getting the same result that we got for f prime at -4. So that ends up being less than 0. Okay? So what are the open intervals on which the function is decreasing? Well, you just go to the intervals where you have a negative symbol, and you say -infinity to -3 union 3 to infinity. And then how about the open intervals where the function is increasing? Perfect. -3 to 3. Alrighty. So now, just for the fun of it, why don't we look at a graph of this? So open up our calculator. Okay, so let's take a look at the original graph, which was, what, 27x minus x cubed. And, we'll go ahead and keep that derivative graph going. So let's look at this graph. And that's not a fabulous picture of it. So let's go ahead and we'll increase the window for the y values. There we go. That's nicer. All right. So here, let's make a picture of this on our document. Okay, so now let's kind of compare some of the stuff that we've been looking at. So here, remember that in blue we have this is f at x. Actually, you know what I'm going to do? I'm going to keep it as f and y. So remember that the blue graph is f at x is 27x minus x cubed. And then we have f prime at x is our green graph. And that one was equal to 27 minus 3x squared. Now, notice that when the derivative graph crosses the x-axis, when it zeroes out, we have a point where there's a relative extremum. So this guy, do you see, is a relative minimum? And where does that occur? Perfect. It occurs at negative 3 rather. And remember how we got C1 is equal to negative 3? And then look over here. At positive 3, we get a relative maximum, right? So on this guy, we end up with how we divide our intervals. So we basically took, actually it would be more like an open circle, right? And we basically said, hey, I'm going to test this interval. That was our minus infinity to minus 3. And look what happened. What was going on with our derivative function on that interval? Good. On this interval from minus infinity to minus 3, f prime at x was good, less than 0. And what was happening with our original function? It was decreasing, right? So here we had, on our original function, it was decreasing, all right? Then here, in that middle interval, right, do you see that f prime of x was greater than 0? And that happened on this picture of the graph going here, right? So this is when our derivative function was positive. And then over here again, we have our original function is decreasing, and notice that our derivative graph is negative. So that behavior went over 2 intervals. Cool? All right. And we did all this without even seeing a picture of the graph. So this is a key part of curve sketching. Okay, so here we go. We're going to identify the open intervals on which the function is increasing or decreasing on this trig function from 0 to 2 pi non-inclusive. All right, so go ahead and pause the movie and see how you do. All right, let's see how you did. So here we go, finding the critical numbers. We have to evaluate f prime at x, right? So remember that we're going to get, using the chain rule, 2 times our something to the 1 power, and our something was cosine at x, and then we need to differentiate with respect to x the inside, which was that cosine at x. And then finishing it up, we will have, or well, almost finishing it up, we'll have minus, and then we'll have negative sine at x for that derivative of cosine at x. Okay, so here we go. F prime at x is equal to 2 times cosine at x, and then d dx of cosine at x is negative sine at x, and then a minus would give us plus sine at x. So we'll get f prime at x is equal to, so I'm going to go ahead and factor out a sine at x. Actually, I could do a negative sine at x, and then we'll have 2 times cosine at x minus 1. So we'll get negative sine. Oh, we have to show the 0, right? So setting the derivative function equal to 0, we'll get negative sine at x times 2 cosine at x minus 1 is 0. So we will have negative sine at x is 0, or 2 times cosine at x minus 1 is 0. And that will yield sine at x is 0, or cosine at x is positive 1/2. So working on this guy first, the sine function zeroes out in the open interval from 0 to 2 pi, just on pi, right? So x is pi, and so we'll get c1 is pi. Here, the cosine function is positive in the first and fourth quadrants, and it has the smallest height when we are, or smallest run, right? The smallest base when we are at a reference angle of pi over 3. So we will get x is equal to pi over 3, or 5 pi's over 3. And so we'll get C2 is pi over 3, and C3 is 5 pi over 3. Are we good? So those are the critical numbers. All right, so running the test for the increasing and decreasing intervals, we make our number line. And what else? We divide that number line up by the, actually, should I have made a number line with arrows at the end? No. I should have made a number line like something like this, either with open circles or like that. So this would be 0 and 2 pi, which were the non-inclusive endpoints, right? Right in the middle, we have pi, and then pi over 3 is over here somewhere, and 5 pi over 3 would be about here. So these are the intervals that we're interested in. So this guy goes from 0 to pi over 3 non-inclusive. Then we're going to have from pi over 3 to pi non-inclusive, pi to 5 pi's over 3 non-inclusive, and finally 5 pi over 3 to 2 pi non-inclusive. So we're going to have 4 intervals to test. So I hope you've been seeing a trend where you get one more interval than you have critical numbers, right? That's always sort of a good, way to check to make sure you've got everything going well. Okay, so let's rewrite what our derivative was. So I'll rewrite that over here. So f prime at x was equal to negative sine at x times 2 cosine at x minus 1. So here we go. We got to figure out our test values, right? So usually, it's in trig land, it's nice to use quadrantal functions. So over here, it'd be nice to use pi over 2. And over here, it'd be kind of nice to use 3 pi over 2 as a test value. And in these, you can take your pick. Let's see, pi over 3, you could use pi over 6, or you could use pi over 4. I'll just go ahead and use pi over 6. And then similarly over here, we can use 11 pi's over 6. Okay, so let's do it. f prime at pi over 6, so we're testing our first interval, is negative sine at pi over 6 times 2 times cosine at pi over 6 minus 1. So f prime at pi over 6 is, so again, we are plugging in wherever we see an x in our derivative function. For this one, we're plugging in pi over 6. So now we will have sine at pi over 6 is a half, so we'll have negative a half times 2 times 3 square root of 3, over 2, and then minus 1, which will give us negative 1/2 times the square root of 3, which is bigger than 1, minus 1. So you'll have a negative for your first factor, and in the parentheses, you'll have a positive. So this is going to be less than 0. Okay, next up, we will have f prime at pi over 2. So this will be negative sine at pi over 2 times 2 times cosine at pi over 2 minus 1. And again, wherever there was an x in the derivative function, we're plugging in pi over 2 this time. So f prime at pi over 2 will be negative 1, and then times 0 minus 1. So a negative times a negative is a positive, so this will be greater than 0. So we'll put a positive here. And f prime at 3 pi over 2 will be negative 1 times 0 minus 1. So now you'll have a positive times a negative, so you'll get a less than 0. So there'll be a minus sign here. And then f prime at 11 pi over 6 will be equal to negative sine at 11 pi over 6 times 2 cosine at 11 pi over 6 minus 1. So f prime at 11 pi over 6 will be negative a half times, it'll again be, well, I'll just write it out, 2 times root 3 over 2 minus 1. So negative a half is positive. These guys are going to divide out, and root 3 minus 1 is positive. So this guy is going to be greater than 0, so that'll be a positive. Now, you might have started noticing a trend that oftentimes the signs alternate. And that's going to be true a lot of the time, but it's not true all the time, okay? So here we go. Now it's easy as pi. By the way, happy Pi Day. Today is March 14th. So here we go. Let's find the open intervals where the function is decreasing. So you just look at the intervals where there's a minus. So we've got from 0 to pi over 3 union pi to 5 pi over 3. And the positive intervals were the other two, and that was from pi over 3 to pi union 5 pi over 3 to 2 pi. And these are all non-inclusive. Okay, so now let's take a look at the first derivative test, okay? All the first derivative test says is, hey, if, first of all, you've got a critical number, which means that, that domain value, it's part of your domain of the graph. C exists on your graph, and f of c exists on the graph. So if you have this critical number, and if the intervals alternate, so you go from negative to positive, right, or positive to negative, you'll have a point where there is a relative extremum. So if you go from negative to positive, so think about going down the hill to up the hill, you would have a relative minimum. Good. So if you go from negative to positive on your derivative at a critical number, then f has a relative minimum at c, f at c. Now think about going uphill to downhill if you're driving or on a bike or whatever. Then you're going to have a relative grade, a relative maximum. So if your derivative function changes from positive to negative at a critical number, then you have a relative maximum. Now, sometimes you get this weird stuff that happens where you get a critical number, something's going on, but it's the same sign on either side. And if that's the case, then it's neither a relative minimum or a relative maximum, just something funny's going on there. So here's a visualization. So this is where you have a relative minimum. So the graph is decreasing to increasing, meaning the derivative is going from negative to positive at the critical number. Over here, it's increasing to decreasing, right? So you've got the derivative going from positive to negative. This is the second figure here. And then you'll notice you have a relative max. And here, this was and that was at, C, f at c. And here, this is a relative min at c, f at c. So over here, if you notice this third one, you've got a derivative that's positive on both sides. So there's something, interesting, right? See how there's this bit of a bobble, but it's not the case where it is a relative extremum. And same on the right side, both sides negative. Okay? All right, so here we go. Why don't you guys go ahead and pause the movie and take a look at this guy. It starts just the same. And then we'll play the movie and see how you did. Alrighty, let's see how you did. We need to find the critical numbers of G. So one way is finding the zeros of the derivative, right? So if we say G prime at x is equal to, so we'll get 2/3 times x to the negative 1/3 minus 0. And so finding the zeros of this, so I'd end up with 0 is 2 over 3x to the 1/3. And remember, the easy way is just to equate the numerator to 0. And does 0 ever equal to 2? No, it's not possible. So, no critical numbers at, or I'll say when, f prime at x is 0. So what do we do? What was that other thing? Oh yeah, there was something about when that derivative does not exist, right, at a point that is a point on the graph. And didn't we talk about what happens when you have some, a function, a rational function where you've got an even over an odd power? Exactly. There's a cusp or bounce. I think of it as a bounce at x equal to 0. You're going to have this cusp or bounce right at x is 0. So on one side, the derivative will be negative, and then instantaneously it'll change to positive. And at a value like that, you don't have something which is continuous but not differentiable. All right. So just hold that thought and recognize that c equals 0. So c equals 0. 0 is our critical number. And we'll look at a picture of this guy very soon. So then we run the test for increasing and decreasing intervals. So if you look at the original domain of x to the 2/3, it's going to be all real numbers. Right? We had a critical number when c was 0, or when x was equal to 0. And so we just have two intervals, minus infinity to 0 and 0 to infinity, all non-inclusive. And our derivative function was g prime. Oh, and you know what? I forgot I had a g here. Let's change this over here to g prime. So g prime at x was equal to 2 over 3 times, I'll write it as the cube root of x. And why don't we test -1 and 1? Those will be easy test values. So we'll have g prime at -1 equals 2 over 3 times the cube root of -1, which would end up being -2/3. So you'll get a negative on that interval. And g prime at +1 will be 2 over 3 times the cube root of +1, which is a +2/3. And so on this side, we'll get a positive. So the open intervals, or interval on which the function is decreasing, is just from minus infinity to 0. And the open interval where the function is increasing is on 0 to infinity. Now, applying the first derivative test, right, we have the leftmost interval negative, so we're going down the hill, and then 0's out, so then it's horizontal, and then it goes up the hill. So that would be a point where, or an input value where there's a relative minimum. Okay, identify all relative minima. So we have one relative minimum. So it's when, so let's figure out, we know that at 0, g at 0, there's a relative minimum. And that's going to be 0. And then remember that g of x originally was x to the 2/3 minus 4. So at 0, comma, good, -4, we have a relative minimum. And then identify all relative maxima. If there is some characteristic doesn't exist, you write none. Okay? So make sure on an exam you write none instead of leaving it blank. Okay, so let's take look at the graph and check out what happened. So here, going to our y equals, what did we have? We had, let's do x to the 2/3 minus 4. Okay. And then I think we can do a regular window now. So let's go to Zoom Standard. And see how there's that cusp or bounce and how the derivative graph is behaving, right? Y values. So let's see our X minimum will be, let's do -3 something. And then our Y minimum should be maybe -5, 5. Okay, and so see how it bounces right there at X is -4? So basically, it means that at X equals 0, the derivative does not exist. That, you know, that whole derivative graph has a vertical asymptote there. So okay, so if we look at this original graph, what happens here is that this bounce right here, this cusp, it's officially called a cusp, but whenever there's a bounce like that, the derivative won't exist at that value. And so that's a picture of what was going on. And, you know, long story short, you might want to just memorize that when you have a rational function that's got in the power an even over an odd, you're going to get some sort of a cusp. Okay. All right. So next up, we've got the graph of some function f is given. The grid goes from -10 to 10 on both axes. You know that wherever you have a point of relative extremum on the original function, you're going to have an output of 0, right, on the derivative function. So that's usually my first step, right? I plot those because these are, you know, points where there's a relative extremum. So then what the derivative function, the graph of it is the graph of all possible what's of the original function. Perfect. Derivative is slope, right? So it's all possible slopes of the original function. Okay, so let's check out, you know, these possible slopes. So one way to do this is you could pick an input value on graph, right? So let's pick this input value. This looks to be at -8, comma, what is that? +3, right? And then let's make ourselves a very small tangent line here. And what we want to do, let me see if I can make this bigger. Let's go a little bigger. And so what we want to do is this. We want to figure out, okay, right at this input value, what's the slope? It seemed to go something like this, right? And so if we made ourselves a slope triangle, to see where it cornered, right? The slope would be, we'd be going down, so negative direction, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over about 2. So at this input value, we'd have of -8, we'd have an output value on the derivative function of -5. So 1, 2, 3, 4, 5. You guys okay with that? Let's take a look over here. Same idea. Let's take a look over here. We've got this point. And again, looking at a tangent line, you see it's less steep. So you'd have a slope triangle, something like this. So you'd be going down 1, 2, 4, 5, 6, and over 2. So at this input value, so this on the original graph was the ordered pair, negative 6, and then 1, 2, 3, 4, 5, 6, negative 6. We are going to have a slope of 3. This one had an ordered pair. It was at negative 8, and the slope we found over there was negative 5. Here at negative 6, our slope we found to be negative 3. So this is negative 6, negative 3 on our derivative function. Here, going to that positive side, right? What's happening is, looks more like our extremum would be here, right? All right. So then basically, going to this other side, if we looked at this ordered pair, right, on this original graph, it would be at negative 1, 2, 3, negative 3, and then down at negative 7. And so if we look at our slope, our tangent line thing here, you know, we could say that our slope triangle is something like 1, 2, 3, down to the left 1, positive slope of 3. So it would be at 1, 2, 3, negative 3. We'd be at positive 3 on this graph. Negative 3, positive 3. And then finding some more values. I mean, you just kind of go through and estimate the slope. At negative 1, when x is negative 1, we're here at about negative 1, negative 1. And so then our tangent line would look like something like this. That would be something, our slope triangle. So then we'd have 1, 2, 3, 4, 5 up and 2 over. So we'd be about at 2.5. At negative 1, we'd be up at about 2.5. And so this ordered pair is negative 1, 2.5. So do you kind of see the trend here? Right? It's going to go back down. This part's a little odd right here. It looks like, you know, it'll still keep getting more steep, but maybe not super fast. Something like that. And then let's see, let's get a couple, you know, some ordered pairs on this side. Looking at positive 1, we're at positive 1, negative 1 for this guy. And then if we drew a tangent line, it would be, we'd have this slope triangle, so 1 to the right, and then 1, 2, 3, 4 down. At positive 1, we'd have an output at negative 4 on our graph. 2, 3, 4. And then over here, this is at 2, negative 8. Making again a tangent line. So we'd be 1, 2, 3 down, 1 to the right. So we'd have negative 8 would be at negative 3. Or I'm sorry, at positive 2. 1, 2 would be at negative 3. 1, 2, 3. All right, so do you sort of see this trend here? So here, something like this, right? Actually, there's probably somewhere around here. And then this guy, okay? We need to test a value on this side, at least one. So here we'd be so 1, 2, 3, 4, 5, 1, 2 to the right. We'd have a positive slope of 2.5 at this input value. Here we'd be up at 2.5. And then if we looked more, I don't know, over here, that's about halfway in, and this would be so 1, 2, 3, 4, 1, 2, so about 2, something like that. And so it looks like it's going to also start sort of leveling out a bit. And so it would look something like that. That's probably not perfect, but the derivative graph would look something like that. So I know it looks like a mess, but that green graph, I'm basically just estimating points on that graph using the slope, using slope triangles. I think that wraps it up for today. Yep, have a fabulous rest of your day. Bye-bye.